Next section, 1.4, sketching graphs of functions. Now, key here to understand is that we are going to be taking current functions and transforming them based on the transformations that we have learned in the past. Reviewing some of those, there's A, which is outside the function. This is a vertical stretch by A. K, which is inside the function. This is a horizontal stretch by 1 over K. C is also inside the function. It is C units either right or left. And D, which is outside the function, it is D units up or down. There's a couple things that we need to understand here. A and D are outside of the actual function. F is representative of the function. A and D are outside the function. And look, A represents the vertical and D moves it up or down. So whatever is outside the function is actually affecting your Y values because it's moving it up or down. It's a vertical stretch and it's a vertical shift. Whatever is inside the function, K and C, two things. They are affecting your horizontal or the right left, meaning the X values, and you're going to do the opposite. This is multiplied by K, so we're going to multiply by 1 over K. If this was a minus 4, meaning negative 4, you're going to go right by 4. If it was X plus 4, then you would go left by 4. So we're going to do the opposite when it comes to the inside the function, meaning the X values, and exactly what it says for A and D. Before we actually get into examples of application in terms of how this is going to affect our graph, I do want to take a minute to make sure we understand what I mean when I say inside the function versus outside the function. So if we have a function given by square root of x, what is inside the function would be given with, as an example, x minus 4. The addition, subtraction, multiplication, or division, or any operation that's happening inside the square root would be considered inside the function, just like it's inside the f. And then anything that is happening outside the function, so 3 times the square root of x minus 4, this would be vertical because it has nothing to do with the function itself. You take the result of the function and you multiply it by 3. So you take the result of the square root and then you multiply it by 3. Whereas in f at x, before you can apply the function, which is square root, you have to subtract by 4. We have to keep that in mind because there's going to be some questions. It's going to be very important to understand the difference between what is inside the function and what is outside the function. Because whatever is inside the function is going to affect your domain, your x values, and it's all horizontal. Whereas what's outside the function is going to affect your y values or your range. One last thing before we shift over to the laptop and start looking at how they actually perform these transformations is the table of values. We know that A and D affect the y values. What they're going to do is for the y values, you multiply by A and you add or subtract D, depending on what the equation is. For the x values, you multiply by 1 over K, or you can say divide by K, and then you add or subtract the C values. So whatever equation you have, in order to determine what's happening to your table of values, you would just take the base graph and apply these transformations. All right, now we're going to go on decimals to get a better understanding of how all of these different stretches or transformations are going to affect the general shape of the graph. Remember that this is sketching graphs of functions, so we're not looking for exact values. We want to get a better understanding of how the general shape is affected. So we'll start with our main parabola. It's y equals x squared. This is the parent function. For the next, what we're going to do now is we're going to see what happens when we add in a minus 2, x minus 2 inside the function. We know this to be a horizontal shift, so it literally takes the graph and it shifts it to the right by 2. There's no change in what the graph actually looks like. There's only a change in its location. Now what we want to do is we want to add a horizontal stretch of 2. What does the graph do? So that horizontal stretch of 2 shrinks it by 2. It makes it, instead of being wider and narrower and taller, it's going to make it narrower, right? And it'll go up a little bit higher, faster. Let's look at a vertical stretch of 3. Again, it does a very similar thing to a horizontal stretch of 2, which is technically a horizontal stretch of 1 over 2. So again, it will make it go higher. It will be narrower than the original function. Let's look at x squared minus 4. We know that this minus 4 is outside the function, so it needs to be a vertical shift. And if we plug it in, what does it do? It takes the same graph, but shifts it down by 4. Now, all of these various transformations combine to give you the final graph, which would be there. So all of those transformations combined would take your original red function, shift it to the right by 2, down by 4. Then there'd be a horizontal stretch by 1 over 2 and a vertical stretch of 3, which would both combine to make our graph actually quite narrow, and that's how you would find your final function. Let's apply some of what we just looked at. So number 1, use transformations to help you describe the characteristics of the transform function. What we're going to do is we're going to start by looking at the characteristics of the parent function. We know domain and we know range because it's a square root function. Essentially are going to be x is greater than or equal to 0 and y is greater than or equal to 0. We know that the square root of x, it has no symmetry. In terms of end behaviors, we know that as x approaches infinity, y approaches infinity. Let's look at what happens after a vertical stretch of 3 and a vertical shift of 2 units down. We know that if this was our original function, this is y equals root x. To see what 3x minus 2 would be, it starts down here and it would be more stretched out vertically. This would be 3 root x minus 2. So essentially the graph looks like it would be pretty much the same in all categories except the range. The range would be YER such that y has to be greater than or equal to 2. All the other characteristics essentially would remain the same. Let's now look at the second example. Describe the order in which you would apply the transformations defined by y is equal to negative 2 f at 3x plus 1 minus 4 to f at x equals root x. Then state the impact of the transformations on the domain, range, intervals of increase, decrease, and end behaviors of the transform function. So we have this as our parent function, and these are the transformations that are happening. Let's first understand what the transformations are. The negative 2 is a vertical stretch plus a reflection over, man, this is not writing well at all. Let me go ahead and turn the keyboard. So a vertical stretch plus a reflection over the x-axis because it's a vertical reflection. The 3 is a horizontal stretch by 1 over 3. We have the 1 would be a shift 1 unit to the left, and the negative 4 is a shift 4 units down. So our original function again is root x. What do we know about the domain, the range, the intervals of increase and decrease, and the end behaviors? So for y equals root x, for our parent function, we know the domain is x is greater than or equal to 0. We know the range is y is greater than or equal to 0. We know the interval of increase is the only one that exists, and that would be from 0 till positive infinity. It starts at 0 and it goes on in that way. It starts at 0 and then it has an upward trend. There is no interval of decrease. And for the end behavior, there are two sides. There is as x approaches 0, which would be the left side because it does not go beyond the 0 here. What does y approach? And then as x approaches positive infinity on the right side, what does y approach? So as x approaches 0, y approaches 0. As x approaches positive infinity, y approaches positive infinity because it's going up. So we have our characteristics for our base function. Now what we're going to do is determine the same characteristics for our transformed function. -2 square root of 3x plus 1 minus 4. Now, if we were to look at it, this is a vertical stretch of -2 and it's a reflection. What that's going to do is it will not affect the domain, but the range, instead of going instead of going up, now that it's been reflected, it's going to go down. So the domain will be one thing. The range is going to be y is, remember, the real numbers, such that now, instead of y being greater than something, it will be less than or equal to something. What is that something going to be? Well, I know there is a shift of 4 units down, so it's going to be y is less than or equal to -4. For the domain, normally the domain is x is greater than or equal to 0, but now my function has been shifted 1 unit to the left, so the domain will be x is a member of the real numbers, such that x is greater than or equal to -1. Okay, let's look at our interval of increase. Again, now that the function has been reflected and it is now trending downwards, there is no more interval of increase. Instead, there is only an interval of decrease. The interval of decrease is now going to go till infinity, but we have to look at where it starts. Instead of starting at 0, it starts at -1 and it goes till infinity. As for our end behaviors, as x approaches -1 would be one of them, and as x approaches positive infinity would be the other one. So as x approaches -1, I know that my y value is going to approach -4, and as x approaches infinity, y value would approach. So as x approaches positive infinity, y approaches negative infinity. Let me go ahead now and turn this into a graph so that we can see how I got the domain, range, interval of increase and decrease, and the end behavior. So I have a function that is shifted 1 unit left and 4 units down. So this same graph here has been shifted 1 unit left and 4 units down. This is where it starts. There has been a horizontal stretch by 1/3, meaning it's now being compressed, and it's been stretched vertically, and it's now opening downward. So it would look something like this. All right, we're looking at sketches, so I'm not concerned about the exact values of the x and y coordinates. I want a rough estimate of what the shape of the graph will be. Now that I see this is what it's going to look like, domain makes sense. X has to be greater than or equal to -1 because x is going to be everything from -1 onwards. The range has to be y is less than or equal to -4, which again makes sense because it starts at -4 and then goes down from here. If I look at interval of decrease, well, it starts at -1 and all the way till when x is infinity, the graph is decreasing. Therefore, there's only an interval of decrease. And then end behavior, there are two ends. One is as x approaches infinity, and the other one is as x approaches -1. And we can see what the y values are approaching for each one.